Okay, so in this next video, we want to look at some direct proofs that are not just about odd and even integers. And so in order to do that, we're going to um, prove some inequalities involving real numbers. So this is the kind of thing that is really important in analysis. So if you take MAT 320, which is a required course for math majors, this kind of proofs involving inequalities is really important for that kind of class. Now, in order to state some of these results, we're going to need to use the real numbers. So here we use this Blackboard R, which is the real numbers. Now, for the real numbers, I can't list them out like I did for the integers, and I don't want to give a really precise construction here of the real numbers, but I'm just going to use the intuitive idea that you're already used to the real numbers. Basically, this is any number that can be written as a decimal. So in particular, any number that can be written as a fraction, um, but also any number that can be written as a decimal that maybe does not have finally many decimal places. So something like pi, which has infinitely many decimal places, or anything that can be written as a decimal. Okay, so we'll be more precise about this in analysis and things, but for now that's fine. And you're already kind of used to the real numbers. That's what you've done and worked with in a lot of math classes such as calculus. And what we want to prove here by a direct proof is we're going to call proposition 5, which is if you assume that x and y are real numbers, and specifically I want them to be non-negative, then if x is bigger than y, then square root of x is bigger than square root of y. Okay, well, starting with a not too surprising fact, hopefully, but we're going to see how to prove this. And again, let's just play a little bit, make sure we're happy with this. So for instance, if we start with 9, which of course is bigger than 4, then the point is that if you take the square root of 9, of course you get 3, and that's bigger than 2, which is the square root of 4. Okay, and just to play again, if I take 100, which is bigger than or equal to 81, then the square root of 100 is 10, and that's bigger than 9, which is the square root of 81. Notice when you take square roots, though, the numbers get much closer to each other, right? 10 and 9 differ by 1, yet 181 differ by 19. So anyway, that's something that you can notice, but it doesn't really matter because even though they get closer, they retain their order property, right? So square root of x remains bigger than square root of y. Okay, just to practice the logical structure here, if I rewrite the proposition in a certain way, I could say that x comma y are real numbers and x and y positive and x is bigger than y implies that square root of x is bigger than square root of y. Okay, so here the logical structure is that this entire thing is what I'm going to call A, and that statement implies the conclusion, which is B. So here we just want to note that sometimes A, the first part of the implication, can be a composition of a few different things, right? So x and y have to be real, they have to be non-negative, and x has to be bigger than y. So there's sort of 3 assumptions that go into the first part of the implication, and then it implies one conclusion, which is square root of x is bigger than square root of y. Okay, so let's look at the proof sketch now, because now maybe we're not surprised by the fact, but that doesn't mean we have an idea of what we should do to prove this. So let's see. Well, first of all, when we say that x is bigger than y, right, that's the assumption we get to work with. Well, notice that this is equivalent to saying that x minus y is bigger than 0. And it's helpful to bring the y to the other side just because now I have something to try to do algebra on. Okay, so again, when you're trying to come up with a proof, there are no steps to follow per se, right? You have to be willing to try something, and when you try it, it may not work, and you have to be willing to try something else, right? So there are no steps to follow that will always work. You have to be willing to be a little bit experimental until you figure out what the right idea is. So I'm not 100% convinced. You might not be 100% convinced that writing it as x minus y is helpful, but it doesn't hurt. And now we're going to play around. So the next question we want to ask, because somehow I'm supposed to take this assumption and say something about square roots. So I know that I have to somehow introduce square roots. So how do we introduce square roots into the expression? Yeah, and the point is that you can actually factor x minus y. It's not something you would normally factor because um, you don't feel like x and y can be broken down into smaller pieces. But of course, I can rewrite x as square root of x squared, and I can rewrite y as the square root of y squared. And now it looks like the difference of two perfect squares, which is perfect for factoring. So I can rewrite it as square root of x plus square root of y, and I can rewrite it as square root of x minus square root of y. Okay, great. And so maybe that's helpful because now I see at least some terms involving square roots, right? And we want to notice that the first term, square root of x plus square root of y, that one we conclude is positive very simply. So since x and y are both positive, by the way, that x, y being positive makes it so that the square roots make sense at all, right? So we actually needed that to even take the square roots like we did above. We should keep note of that when we write the proof itself. But since these things are positive, then we know the square root of x plus square root of y is also positive. Basically, anytime you take a square root, you had to start with a positive number. The square root we know is positive. So you add two positive numbers, you remain positive. So that's not, there's nothing to do there. And so then the point is that we're going to use the fact that if x minus y is positive, then the product here is positive. And since the first part of the product is positive, we will be able to say that the other piece must also be positive. Which implies what we want, right? Okay, but again, this is a sketch. We're being very informal. This is not a proof, but now we get the idea. So now we can go from a sketch to an actual proof, okay? And so in the proof, we have to write this a little more carefully. Okay, so first we should start with our assumptions. So assume that x and y are real numbers, x and y are both positive, and x is bigger than y. X being bigger than y is equivalent to x minus y being bigger than 0. Just pointing that out to the reader. Now, by rewriting x as square root of x squared and y as the square root of y squared, we find that the square root of x squared minus square root of y squared is bigger than 0. Okay. Okay, sorry about that. I think my iPad is playing tricks on me. Let me start the proof again here. So assume x and y are real numbers. X comma y is bigger than 0, and x is bigger than y. Okay, x being bigger than y is equivalent to x minus y being bigger than 0. Okay, now by rewriting x as the square root of x squared and y as the square root of y squared, we find that square root of x squared minus the square root of y squared is bigger than 0. So by vectoring the left-hand side, of this inequality, we find, okay, so now we rewrite this as the square root of x plus the square root of y times the square root of x minus the square root of y, and that's bigger than or equal to 0. Okay. Okay, so now we want to notice, so since x and y are both positive, we know that square root of x plus square root of y are both positive. We're using the fact that x and y are positive to show that the square roots are well defined, but also then square roots are also positive, and so the sum of two positive things is positive. Now I'd like to divide both sides by this quantity. The only thing I'm worried about is when x is 0. So we just want to notice that if square root of x plus square root of y is equal to 0, the only way that can happen if you sum two non-negative numbers and get a 0 number, they both must be 0. So then square root of x equals 0 and square root of y equals 0, which implies x equals 0 and y equals 0. And we just want to notice that in this case, square root of x is clearly bigger than or equal to square root of y. Okay, now we're technically doing a proof by cases now, but in this case, I'm not even separating it out because I consider it like a very trivial edge case that we just need to notice to the reader that if they're both 0, then this is clearly true, right? So if that means now we can assume that x plus y is strictly positive, then let me call this star, then we can divide both sides by square root of x plus square root of y to find exactly what we want, right? Which is square root of x minus square root of y is bigger than or equal to 0. And we just want to point out to the reader, which implies that square root of x is bigger than square root of y as desired. Okay, so that's our first example of a direct proof involving inequalities. And here we had to factor this inequality in a way that we wouldn't factor usually in an algebra class, but was convenient for the proof. And we had to consider a sort of edge case where square root of x plus square root of y is equal to 0, but we showed that in that edge case, x and y have to be 0. So it's a very, very particular case that that happens. And we got rid of that case and shown that it was clearly true in that case. And then every other case, which is where square root of x plus square root of y is strictly positive, then we can divide both sides.